we'd like to do is to continue our discussion of polynomial functions and equations. All right? And let's look at an idea. For example, if we had the equation x squared plus 1 is equal to 0, and x is over the set of real numbers, what was our conclusion about a sentence such as this? And what have we been saying about the solution set of x squared plus 1 equals 0, where x is a real number? What can we say, Doug? This is indeed the empty set. And as soon as we then extend our number system to include x over the set of complex numbers, what then did we say about the solution set to this equation? And can anyone just look at this and think of those roots? Tim?
1i.
1i, all right, we have the number I, and in fact I think there's another number
Negative 1i.
in which we have also negative I, is that right? Would then be the solution set of this equation over the set C of complex numbers. Now, in fact, there's a very basic theorem that we are going to rely on. It's so fundamental that it's given a special name called the fundamental theorem of algebra, all right? And what that theorem says is that every polynomial equation, all right, let me abbreviate here, every polynomial equation with complex, notice it says with complex coefficients, has at least one complex root, all right, at least one complex root. And this is indeed what we call the fundamental theorem of algebra, and let me just abbreviate this, of algebra, which is quite a famous theorem actually, and it's an existence theorem. It has to do with there exists at least one complex root. All right? Now, what we'd like to do, for example, suppose r sub 1 were that complex root. Then x minus r sub 1 is going to be a factor. Isn't that right? And whatever is left here, think of it as some q of x then is equal to 0. The fundamental theorem tells us that indeed for that function, for that q of x is equal to 0, there's at least one complex root. Call that one r sub 2. And then whatever is left, there's at least one for that. Call it r sub 3. And the product of all of these down to some, say, x minus r sub n is then going to be equal to 0, where n is going to determine what number. What would n be? N would be the, Malcolm? The degree of the polynomial, and I think you may conclude that we may write it in this pattern. And what conclusion can we then come to but that every polynomial equation with complex coefficients and of degree n greater than 0 will have what? What then do you think we may conclude from that? We'll have, Bill?
N roots.
We'll have exactly n roots, all right? And let's indicate that as a theorem. We're not going to prove these two statements, in which we have here every polynomial equation with complex, notice now we are over the set of complex numbers, with complex coefficients of degree, let's include that, n greater than 0, has what? Has exactly n complex roots. Now you and I have seen examples, for example, x minus 1, the quantity squared equals 0. That happens to be a quadratic, and how many roots? What are the roots of x minus 1, the quantity squared equals 0? What number or numbers will make that true? Bill?
1 is the double root there.
1 is a double root, and if we include that case in which we then think of that as one root, but of multiplicity 2, or a double root, indeed it will also satisfy this theorem as we have right here. Well, let's look at a second idea. Let me call this one number 2, and this is our first idea, so then let's look at a third idea. If 2 is a root of this cubic equation, what are the other two roots? Well, let's see now. If we then were to use our synthetic division, and we then will have 2 here, and what then are our coefficients? We have what? 1, negative 8, 22, and negative 20. Is that right? And we bring down the number 1. There's 2 minus 8 is a negative 6. Negative 12 plus 22 is 10. And 20 minus 20 is 0. And sure enough, 2 then is going to be a root. We then have x minus 2 times. What then is q of x? The other polynomial here, which is of reduced degree. Kirby?
x squared
x squared
minus 6x
minus 6x
plus 10.
plus 10 then is going to be equal to 0. Now rather than repeating this process, we can now, since we have a quadratic here, let's go right to the quadratic formula and solve this then for 0, all right? We have then x is equal to the opposite of b plus or minus the square root of b squared minus 4ac is what number?
40.
Minus 40 all over 2. And that then is 6 plus or minus the square root of what number? Negative 4 all over 2, which is 3 plus or minus 2i. Let's see, now this were simply the number I. Is that right? It's 6 plus or minus 2i all over 2, which is 3 plus or minus I. Well, notice now we may write our products here then. If 2 is a root, and if 3 plus I is a root, and 3 minus I is a root, then x minus 2 times x minus the quantity 3 plus I times the quantity what? X minus a 3 minus I is then going to be equal to 0. Now, notice what we have started with here, but a polynomial equation in which the coefficients are what kind of numbers? The coefficients are real numbers, is that right? Are real numbers. And 2 is a root, and notice now, suppose we were to look at 3 plus I as one of the roots. What must occur in order to, when you do this multiplication and you multiply it all out, what must occur for the other root in order to end up with real coefficients there? What do you think you have to have, Malcolm?
Complex conjugate.
You have to have its complex conjugate. In other words, if 3 plus I is going to be one of the roots, 3 minus I has to be the other one, another one, in order to make this product such that the product of the two is then going to end up to be a real number. Is that right? So in fact, we may state that as a theorem in which, what then do we want to say? If a plus bi is a root of a polynomial equation with what? What is the important word here? With real coefficients. With real coefficients, then what is our conclusion? But that, what do we want to say? Kirby or Brenda?
A minus bi is another root.
A minus bi is also a root. Very good, all right? And this then enables us, as we explore polynomial functions and equations, this enables us, these three theorems as we have here, will enable us to determine what those roots are. Well, let's look at another idea in which here we have we're asked to graph this polynomial, which happens to be a cubic. P of x equals x cubed minus 3x plus 1. Now, we've learned how to graph linear functions, certainly, which are, those graphs are straight lines. We've learned how to graph quadratic functions by that completing the square method. It always turned out to be what kind of a graph? A parabola. And now what we'd like to do is to consider the graphs of polynomials greater than of degree 2. All right? And here we have, for example, a cubic. Well, this method of synthetic substitution, synthetic division, certainly will help us find lots of ordered pairs of numbers. We know that it's a cubic, and since the coefficient here is a positive number, we know that it must increase from left to right, and we have some idea of what the graph is going to look like. Let's come down here. Before the lesson started, I made a table in which, from our synthetic substitution method, if x were 0, here are our coefficients of 1, x cubed, plus 0x squared, minus 3x, plus 1. All right? So that when x is 0, p of 0 is 1. Now when x is 1, if you go through your synthetic substitution, you end up with p of x to be negative 1. And so on. I did this for a number of values. Now, with those values, and realizing what we know about a cubic function, let's turn over here to this coordinate axis in which I've actually made its graph. And I think you will agree that the graph is going to look something like this. Perhaps the degree of accuracy of our graphs is relatively unimportant. What's more important, I think, is the shape of it, certainly, and a general understanding of what's going on. For example, in this case, notice that the graph is going to cross the x-axis how many times? 3. And it's going to cross the x-axis 3 times. So therefore, looking at our, just coming back here, looking at our function, the zeros, how many zeros are there going to be for this function? There are going to be 3 zeros. Now remember the P over Q theorem that had to do with the corresponding equation. The only possible rational roots for this would be what numbers? 1 and negative 1. Let's now come back here to our table. When xa is 1, P of 1 is negative 1, and that certainly is not 0. And when what? When x is negative 1, P of negative 1 is 3, and that's not 0. So indeed, what's our conclusion about the zeros of this function? They're not rational. But the fact that it crosses the x-axis 3 times determines or says that they must be what kind of numbers then? They're certainly going to be, what? The fact that it crosses the x-axis makes it what kind of a number?
Real.
It makes it a real number. But if they're not rational, and if they're real, therefore what kind of numbers must they be? They're going to be 3 irrational numbers. And this kind of analysis is what is required as we continue our exploration of functions of degree greater than 2. Well, before we continue that, there's another idea that I think is worth looking at. Now, the fact that we have made a nice smooth curve here on our graph is a very important and big assumption that we have made. For example, suppose I were to take some value right here on the curve, let's call it A, on our x-axis, and associated with this height there is, right at this point on the curve, is some number. Let's call that number, let's call it P of A, all right? Now, let me go away from A to the right some amount, it doesn't matter where, and let's decide to call this number right here, let's call it B. So that associated with this point is going to be the coordinate of what? The point will have coordinates of what? P of B, right? In fact, you may think of that as this length. That's our second element of our ordered pair, where B is the first element and P of B is the second. Now, let me take some number, M, say, where M is between P of B and P of A, all right? And if you thought of this geometrically, you're going to think of some length of line segment, which must be a length which is between this length and that length. Is that right? Okay. Now, where must this point here be? Let's call this point C. Where must that point C be? Certainly it's going to be where? Between A and B. And I think you will agree that there exists some number C where C is between A and B such that P of C must be equal to what number?
M.
P of C, if this is the coordinate of C right there, P of C must be equal to M. Very good. And in fact, this is quite an assumption that we are making here as we make our nice smooth curves, and it's given a special name, and it's called a property of continuity. So let's write this down and state what it is. The property of continuity, all right? And what it says is that for every, again, notice we're talking only about polynomial functions here, although this property certainly holds true for other functions, which we'll investigate later on. For every polynomial function or formula, all right, of if M is a number, all right, let's see how we may say it, such that, now what do we want to say about M? Such that M is between where and where? Between P of B on that side and P of A here, all right? There exists, how do we want to say it? There exists what? Some number C where must C be? Between A and B, such that, and this then is our conclusion, such that what holds true, but that P of C is equal to M. And from this statement, it then will enable us to arrive at every point on this graph. And that will then enable us to make a nice smooth curve. Okay? Well, let's come back to the idea of looking at the zeros of this function as we have here. Now the fact that we do have a nice smooth curve, there are no holes in it, there are no breaks in it or anything else, All right? Now, the fact that the graph is going across this axis indicates that somewhere right in here, say at this point, there must be what? There must be a zero of the function. Is that right? Well, let's see now. Right here at, when x, say, is -1, -1, p of -1 is up at what number? Looks like 1, 2, 3. Is that right? And when x is -2, p of -2 looks like it's at this number, which is -1. So let's come over here and write some of that down. Here we have p of -2 is equal to what number? -1. And p of -1 turned out to be equal to what number? Is equal to 3. Now, what then does our property of continuity tell us? Now notice here that this number, p of -2, is a negative number, and p of -1 is a positive number. Therefore, there exists some number c, call it, all right, such that what? P of c is equal to, and we would like it to be equal to what number?
0.
Equal to 0. Will you agree with that? There is some number c. Well, what then do we call that number c? That's indeed going to be the 0 of the function, and also the corresponding, what? Root of the equation, or the root of the corresponding equation. Well, since we've already used our P over Q theorem and said that it's not a rational number, and since it indeed crosses the x-axis, it must be a real number, what then, again, what kind of a number must it be? But what? An irrational number. Now, certainly, just from our graph, I think you will agree that it's going to be between -1 and -2. Let's try to approximate that irrational number. And looking a little bit more carefully at the graph, you say, well, it might be around a -1.7 or -1.8 or somewhere around there. Now, again, what I'd like to do is to turn to our table, and what I have done here was to make another table using our synthetic substitution. And notice that the arithmetic is getting a little bit messy here. I took values, say, at -1.8. And going through our synthetic substitution process, notice that P of -1.8 is 0.57. And then I took a value of -1.9. And P of -1.9 is a -0.16. So you say to yourself, aha, certainly the root is going to be between where and where? Between, what? It must be between these two numbers, is that right? From our property of continuity, because this value here is negative and this value here is positive. Well, let's see if we can't estimate and determine a method by which we can actually calculate that. What I'd like to do is to now look at this picture. And what I have done here is to enlarge, so to speak, that part of the graph around, here we have a value at -1.8, and notice here the coordinate is -1.8 comma 0.57. Let's call that point B. Right here I have a value of -1.9, and it will have an ordered pair of -1.9 comma -0.16. Now, what I'd like to do is to draw a straight line between points A and B. Now we know that our function is going to be curved in there somewhere, is that right? And if we were to draw a straight line, let's call where that straight line crosses the x-axis, let's call that point C, in which the coordinates of C, let's call it a -1.9 plus some little number h, all right? And its coordinates will be -1.9 plus h comma 0. Now, if we can find this number h, we then can add it to a -1.9, and you think that's a pretty good approximation to this point right here, which is the actual point where it crosses the curve? All right, let's see how we can proceed. And the method that we're going to use is by means of the slope and what we might call a linear interpolation. Okay? Now, let's find the slope of of AC right here. Here we have the slope of AC, this is some segment AC, is going to be equal to, right, this segment, this slope of AC, and what can you say about the slope of AB? They are certainly the same because why? Because they contain the same point, is that right? Namely which? The point, there's AC, I'm talking about AC, and AB, and it's one and the same line, right? They both lie on the same line, so indeed they have the same slope number, and this then is equal to the slope of AB. Now, let's look at the slope of AC. Well, if you remember how we define slope, it's 0 minus a negative 0.16 divided by what? By this number, which is what? Negative 1.9 plus h minus this number. Is that right? Is that our definition of slope? Which is minus what number? A negative 1.9. And this then must be equal to the slope joining AB. Well, it's going to be what? A 0.57 minus what number? A negative, what? 0.16 divided by, and must be what? Negative 1.8 minus what? A negative 1.9. Well, let's clean up our arithmetic here somewhat. Here we have what? A positive 0.16 divided by what number? Divided by h. Does everyone agree with that? Is equal to, and 0.57 minus a negative 0.16 is what number? 0.73 divided by a negative 1.8 minus a negative 1.9 is 0.1. Okay. Now let's multiply through here. Another name for this, let's multiply by 10, say. So 10 times 0.1 is 1, and hence on the right-hand side we have what? 7.3. 0.16 divided by h then is 7.3. H then is going to be equal to what? 0.16 divided by 7.3. Let's multiply this by some number like what? 100. And that then is 16 over 730. Well, let's try to get this to the nearest hundredth of a unit, shall we? Let's do a little bit of long division here. 730 into 16.000. And what then do we have? There's a 0. 730 into 1600 goes what? Looks like it goes twice. So 2 times 0, 6, 14. Check my arithmetic, please. 0, 4, and what? 1, and another 0. Aha, 730 looks like it goes to, the closest number would be a 2, and in fact, since it's, say, to the nearest hundredth, this then is going to be equal to 0.0, what? 0.02. Well, let's then let x be that number, which is our approximation of the root, okay, which is going to be equal to what? A negative 1.9 plus this number of 0.02. And so what number is that but a negative 1.88. Okay, a little bit of arithmetic here. A negative 1.88. Now, that's our first approximation to the root. Well, what I'd like to do now is to make another picture. Let's come back here. And I have now enlarged that portion of the graph. So that here we have a negative 1.88. And in fact, let's now, what I've also done was to have made up another table using our synthetic substitution. Negative 1.88, and p of that number, notice, is 0.004. And I then took the next number of negative 1.89, and it turned out to be a negative 0.077. So indeed, our root must be between where and where? 1.88 and 1.89. I then repeated this entire process and solved for another value of h. Or in fact, you can actually do this. Since we were interested in those values which were to the nearest tenth, or rather say to the nearest hundredth, what then is our conclusion about this number x? You would like to say that this number x is going to be about what value? Right in here, x then is going to be approximately equal to what? Well, let's call it negative 1 point to the nearest hundredth, I think would be 88. Is that right? Because if you look here at 0.004 and this number at a negative 0.077, it certainly would be much closer to negative 1.88. Probably negative 1.882 or something like that. Well, this method certainly lends itself very nicely to a computer program in which you can reiterate this process and get to any degree of accuracy that you want. Actually, later on in mathematics, you're going to learn a much more efficient way of finding and estimating roots of polynomial equations and functions. rather than this method of interpolation. Let me give you your homework assignment for next time. This